Last episode, you built a perceptron from scratch. You saw that without an activation function, a network of any depth collapses to a single linear transformation, no matter how many layers you stack.
The activation function is what gives depth its power. But there isn't just one. There are 7 major options, and choosing the wrong one silently kills your network. I'm Mahaz. By the end of this episode, you'll have a cheat sheet for every activation function, the code to plot them all, and the intuition to pick the right one without guessing. Today, Sigmoid, Tanh, nn.relu, Leaky nn.relu, SiLU, nn.gelu, Swish, what each one does, what problem it solves, and exactly when to use it. Before the functions themselves, why does nonlinearity matter?
A linear transformation maps inputs to outputs with a matrix multiplication. Stack 2 linear layers, W2 times W1 times X. That's just W3 times X, a single matrix. 2 layers bought you nothing. 100 layers buy you nothing. Add a nonlinear activation between layers, and the math changes completely. The composition is no longer linear. Each layer can learn a genuinely different representation of the data. This is why deep networks are powerful, not because of depth alone, but because nonlinear activations between layers let depth create increasingly abstract representations. Every activation function we cover today is a different answer to the same question. What nonlinearity should sit between layers? Each answer has trade-offs.
Sigmoid, the original, the one that started it all.
Formula: sigma of z equals 1 divided by 1 plus e to the minus z. Output is always between 0 and 1. Smooth, differentiable everywhere. The S-curve you've seen in every introduction to neural networks. PyTorch, torch.sigmoid of x, or nn, sigmoid as a module layer. The derivative at z is sigma of z times 1 minus sigma of z, maximum value of 0.25 at z equals 0. The problem: vanishing gradients. At large positive or negative z, the sigmoid saturates. Output is near 0 or near 1. Gradient is near 0. Multiply many near 0 gradients through many layers. The gradient reaching early layers is essentially 0. Training stalls. When to use sigmoid, output layer for binary classification, it gives you a probability between 0 and 1. Almost never in hidden layers of deep networks. nn.relu replaced it there.
Tanh, hyperbolic tangent. The zero-centered upgrade to sigmoid.
Formula: tan of z equals e to the z minus e to the minus z, divided by e to the z plus e to the minus z. Output is between minus 1 and plus 1, centered on 0. PyTorch, torch.tan of x, or nn.tan. The derivative is 1 minus tan squared of z, maximum value of 1 at z equals 0. Stronger gradient than sigmoid at the origin. Zero centering matters. If activations average around 0, the gradients in the next layer don't have a systematic bias direction. Sigmoid outputs are always positive. Tanh fixes this. Still vanishes at saturation, just like sigmoid. When to use: LSTM and GRU hidden states. The gating mechanisms rely on the minus 1 to plus 1 range. In feed-forward hidden layers, nn.relu still usually wins.
nn.relu, rectified linear unit. The function that made deep learning practical.
Formula: max of 0 and z. If z is positive, pass it through unchanged. If z is negative, output 0. The simplest possible nonlinearity. One comparison operation. PyTorch, torch.relu of x, or nn.relu. The gradient is 1 for positive z and 0 for negative z. No saturation on the positive side. Gradients flow freely for active neurons. Why at 1? Computationally free, no EXP calls, sparse activations. Many neurons output exactly 0, which speeds computation. And it just works. ResNet, VGG, most CNNs, most feed-forward networks, all use nn.relu by default. When to use: hidden layers of feed-forward networks and CNNs as your default choice. Start here. Switch only if you have a reason.
nn.relu has one serious failure mode, the dying nn.relu problem.
If a neuron's weights push its input permanently negative, its output is always 0. Gradient is always 0. The weight update is always 0. The neuron is dead. it will never recover during training. In large networks with high learning rates, this can happen to a significant fraction of neurons, silently reducing the effective capacity of your model. Leaky ReLU fixes this with one change. Instead of outputting 0 for negative z, output alpha times z, where alpha is a small constant like 0.01. The neuron can never fully die because the gradient is always non-zero. PyTorch, nn.relu with negative_slope equals 0.01. When to use. Anywhere you're seeing dying ReLU symptoms, large fractions of zero activations, loss plateauing early, neurons that don't respond to any inputs.
YLU, exponential linear unit. Smooth negative region, mean outputs closer to 0.
Formula, z for positive z, and alpha times e to the z minus 1 for negative z. Alpha is typically 1.0. The negative region is smooth, no kink at 0 like ReLU and Leaky ReLU. PyTorch, nn.gelu with alpha equals 1.0. The smooth negative region means the gradient is continuous at 0, cleaner signal flowing back through the network. The exponential saturates toward minus alpha for very negative z, so very negative pre-activations don't dominate the gradient. This can make training more robust on noisy data. When to use. Feed forward hidden layers where you want zero-centered activations without the non-differentiability of ReLU at 0. Trade-off? EXP is slower to compute. Generally outperforms ReLU on classification, but less commonly used in practice.
GELU, Gaussian error linear unit. What BERT, GPT, and most transformers use.
Formula, z times phi of z, where phi is the cumulative distribution function of the standard normal. Intuitively, it gates the input by the probability that a standard normal random variable is less than z. PyTorch, nn.gelu. In practice computed as z times 1/2 times 1 plus tan of the square root of 2 over pi times z plus 0.044715 z cubed. An approximation that's fast and differentiable. Why transformers use it? GELU is smooth everywhere, has a slight negative region like YLU, and empirically outperforms ReLU on language tasks. The probabilistic gating creates useful regularization-like behavior. When to use. Transformer architectures, BERT, GPT, VIT, as a direct drop-in. Also worth trying in feed-forward networks when ReLU or Leaky ReLU underperforms. Slightly slower than ReLU due to the Tanh computation.
Swish, Google's self-gated activation, also called SiLU, Sigmoid linear unit.
Formula, z times sigmoid of z, or equivalently z divided by 1 plus e to the minus c. It's smooth, non-monotonic. It dips slightly below 0 before rising, and unbounded above. PyTorch, nn.gelu, same as Swish. The gradient is sigmoid of z plus z times sigmoid of z times 1 minus sigmoid of z. This means the gradient depends on both the sign and magnitude of z. The non-monotonicity is the key property. Unlike ReLU, Swish doesn't hard zero all negative inputs. Small negative inputs get a small negative output, preserving some information. Empirically beats ReLU on ImageNet at deep network depths. When to use. EfficientNet and MobileNet architectures use Swish by default. Worth trying in deep CNNs as a drop-in for ReLU when you want marginal accuracy gains. Not worth the added complexity for shallow networks.
A preview of a concept that will get a full episode later. The vanishing gradient problem.
During backpropagation, gradients are multiplied together as they flow from the output layer back to the input layer. If each multiplication makes the gradient smaller, as Sigmoid and Tanh do in their saturated regions, the gradient reaching early layers can be effectively zero. Zero gradient means zero update. Early layers don't learn. The network has effectively shallow learning happening only in the last few layers. ReLU mostly solve this. Gradient is 1 for active neurons, so it doesn't shrink the gradient on the positive side. This is the primary reason ReLU enabled very deep networks in a way Sigmoid never could. The full story, batch normalization, residual connections, careful initialization, comes in later episodes. For now, if you see training stalling with very small gradients, switch from Sigmoid or Tanh to nn.relu as the first fix.
The cheat sheet. When to use each activation function.
Binary classification output, Sigmoid. It maps to 0 to 1 probability. Multi-class output, softmax. Not covered today because it's not a hidden layer function, but remember, no activation in the output layer for regression. Hidden layers in feed-forward networks and CNNs start with nn.relu. It's fast, it works, it's the default. If you see dying neurons or the lost plateaus early, switch to Leaky nn.relu. Transformer hidden layers, GELU. It's what every major transformer uses, and it empirically outperforms nn.relu on language tasks. Deep CNNs where you want an accuracy edge, try Swish or SiLU. LSTM and GRU hidden states. Tanh, the architecture was designed around it. nn.relu. Try it when you need zero-centered activations and don't mind the compute cost of EXP.
Now the code. Plot all 7 activation functions in one figure using PyTorch and Matplotlib.
Import torch, torch.nn.functional as f, and Matplotlib pyplot. Create x as torch.linspace from -5 to 5 with 300 points. Compute each activation. Sigmoid, Tanh, nn.relu, Leaky nn.relu with _slope 0.01, SiLU, GELU, and SiLU for Swish. Create a figure with 7 subplots in one row. For each, plot x against the activation output. Add a title and color-coded line. Mark the 0 axis with a dashed gray line. Save as activations.png. Running this gives you a visual reference for every function. The kinks, the saturation regions, the smooth curves. This is your reference image for every network you build from here on. The full code is in the repo. Your challenge: run it. Add annotations for the vanishing gradient region on Sigmoid and Tanh, and post your annotated plot in the comments.
Before episode 9, 6 checks.
Check 1. You can state why non-linearity is mandatory. Without it, any number of linear layers collapses to 1. Check 2. You can describe the vanishing gradient problem and name the 2 activations most prone to it. Check 3. You know the nn.relu formula, its gradient, and the dying nn.relu problem. Check 4. You can explain what leaky nn.relu fixes and why.
Check 5. You know that GELU is what transformers use and can roughly describe its formula, z times phi of z. Check 6. You can fill in the cheat sheet from memory, which activation for binary output, hidden layers, transformers, LSTMs.
6 checks. All pass. Episode 9 awaits. Multi-layer networks and the full forward pass through a 2-layer network built in number PY.
Recap. 7 activations, 1 cheat sheet.
Sigmoid, 0 to 1 output, vanishing gradient, binary output only. Tanh, -1 to 1, 0-centered, still vanishes, use in LSTMs. nn.relu, max 0z, no saturation on positive side, fast, default choice. Leaky nn.relu, fixes dying nn.relu with small negative slope.
SiLU, smooth negative region, 0-centered outputs, slower. GELU, transformer standard, probabilistic gating. Swish, non-monotonic, beats nn.relu in deep CNNs.
Your challenge: plot all 7 with PyTorch and Matplotlib. Add vanishing gradient annotations. Post the image. nn.relu didn't beat Sigmoid because it's elegant. It beat it because it's fast, it doesn't vanish, and it just works on almost every problem you'll throw at it.
Now you have the full picture. 7 functions, their trade-offs, and the intuition to pick the right one. That's not a detail. That's the difference between a network that trains and one that doesn't.
Next episode, multi-layer networks. We stack neurons into layers, trace the full forward pass through a 2-layer network, and build it from scratch in number PY.
Subscribe. Plot your activations. See you in episode 9.